where areas with higher blood flow appears to have lower contrast. And that's the key for this technology. It has several medical applications, including dermatology, transplant surgery, and burn depth analysis. So making a handheld LSCI brings a lot of advantages for both clinical staff and patients. So this is an example of a smartphone-based system. We have one to image retina, and the one which is mounted on a gimbal stabilizer to decrease the amount of movements. And this is the one we have built in, at the University of Twente, handheld perfusion imager. So let's see what we see with this handheld perfusion imager. This is a representative perfusion, a series of perfusion maps. You see that it moves. It doesn't. It's not at a certain position, and that's because of movements, natural movements of hand. So it introduces two problems. The first problem is if we temporally average the number of frames, we see spatially blurred image. And if we look at individual frames, this frame is taken during which movement is relatively low, so it looks normal. We see higher perfusion here, for instance. But if we grab a frame during which the perfusion level is higher, the movement level is higher, we see an unrealistic increased perfusion here, which is a result of, well, movement artifacts. So we have tackled these two problems during these 4 years research. So let's start by addressing this part of the problem. We have explored movement artifacts. What we did, we mounted a probe of an electromagnetic sensor and made normal handheld measurements in order to quantify the amount of movements we can measure. So these are just normal movements on surface movements measured from during a normal handheld measurements in millimeter scale. This is the back cover thesis, the pattern you see there. And we've categorized it into 3 types of translations, tilt, and on surface speeds. For 10 test subjects, you could quantify these movements. And we have also mounted our system on a translational stage and did measurements while having phantoms of different scattering levels. We have observed that lower scattering coefficient causes observation of lower speckle contrast, which means more movement artifacts appear. So the second step of study was about looking at influence of illumination types. So we measured with 3 different types of illumination, namely spherical, planar, and scrambled. Scrambled one is used in commercially available devices. And this is the translational stage I was talking about. We mounted the system on that stage and moved. And we measured quite surprising results, quite a difference between 3 types of wavefronts. We have seen if we apply translations, plane waves cause the least amount of speckle contrast drop. This is also a result of 6 patients. So per patient, patients were asked to perform handheld measurements with these 3 types of wavefront, and we have seen that with plane waves, least amount of speckle contrast drop is resulted. So we tried to then predict these movements by modeling them. So we used a method based on optical Doppler effect. We modeled a range of incoming wave vectors, a range of outgoing wave vectors, and we know that the Doppler shift cause is a result of the variation of incoming and outgoing wave vectors times the velocity. So if you look at top view, we can model these range of incoming and outgoing wave vectors with some circle functions. If we convolve these 2 functions, we can calculate the optical Doppler spectrum. And then in the end, the time-integrated speckle contrast is results of an integration over certain exposure time, inverse Fourier of the power spectral density. So this is a simulation of speckle patterns, dynamic speckles, when we apply 1 centimeter per second. And this graph is an important one that shows speckle contrast in terms of applied translational speeds. The solid curves are the predictions by the model, whereas the dots are simulated parts. So we see that they agree. So we made a prototype and we took it to hospital for patient study, for psoriasis patient study. We developed a pipeline, a data processing pipeline, starting from acquiring raw speckles, going through all the steps to get the perfusion map, which represents, which is a representative of a single measurement. So what we did, we could follow these the movements during handheld measurements by tracking these dots directly on noisy speckle patterns. So if you don't do anything with it, you can see that it's not easy to follow a certain region of interest, whereas when we do track, we can, it's possible that during handheld measurement track a certain area. So as well as tracking an area, we can also compensate this spatial blurring that we see, that if we don't compensate, we don't have alignment, we see this blurry pattern you saw on the first slide. But if we do align, we see a frame which is quite similar to the mounted one. So this is a conventional mounted experiments and a handheld. You hardly see any difference between the two. This is good, but this is not the whole story. If we look at the numbers and compare average perfusion in the lesions for a range of test subjects, we see that for all cases, the average perfusion in handheld case is higher, and the difference is statistically significant. This means that this research should be continued. And with this, I would like to thank you for your attention.
Welcome, and I open this public meeting of the Doctorate Board of the University of Twente. A very welcome to all of you, and in particular the family and the friends of the candidate. And also special welcome to the members of the committee of today. And most of them are here present physically, as you can note. And we have two members who are present in a digital way. And I'd like to shortly introduce them to you. In particular, special welcome to Professor Stirenborg, the University of Amsterdam. And he's a professor. So he is digitally there. He's a professor in biomedical optics and currently working in Amsterdam and at the Dutch Cancer Institute. And we have also available Dr. Sacher, a dermatologist from the Radboud University Medical Center. Also a special thanks to Dr. Tesler from Linköping University in Sweden. He's a clinical physicist. And we have two members from the University of Twente, Professor Offerhaus and Professor Verdaasdonk, and of course the promotor, Professor Steenbergen. Could the candidate and his paronyms please come forward? Dear candidate, are you ready for the defense?
Highly esteemed Rector, I'm ready.
So this was the easiest question of the defense of today, and I would like to give the floor to the first opponent, and that is Dr. Tesler from Linköping University. Dr. Tesler.
Dear candidate, thank you for. I'm glad for the opportunity to be here today, and I've been reading your thesis with much pleasure. I have, of course, a few questions for you. And my first question is about the origin of the movement artifacts that you have been focusing on. You have been focusing on movements artifacts deriving from the operator of the speckle, handheld speckle. Of course, in the clinic, you also have movements artifacts that originate from the patient. And I wonder if you can discuss a little bit if your findings can be applied to movements that arise from the patient as well, or if you consider that these are of minor importance.
My learned opponent, thank you for your compliments and thanks for your interesting questions. As far as I understood, you would like to know about the origin of movement artifacts and especially focusing on the movements caused by patient itself but not operator, and whether our investigation can help to be applied to address that challenge as well. In response, I would like to say that of course, movement artifacts in handheld LSCI is all about relative movements, either operator or patient itself move. You will see, well, two problems: spatial blurring and increased perfusion, measured perfusion because of extra blurring within the exposure time. Well, the first part of our study, we just measured the handheld movements caused by hand itself. So that part, the result of that part is all about how much movement you have when you have a normal hand tremor without severity. But the rest of them, I would say for sure, as long as you have relative movements, it doesn't matter whether it comes from the operator itself or a patient. I know that so many patients cannot stand keep their organ as still as possible. But when we talk about increased level of blurring, it's just about relative movements.
Thank you. So does that mean, according to you, that the optimizations that you have made in your work also help in the reduction of movement artifact arising from patients?
Indeed, yes.
Okay, thank you very much. Then I have one other question. It is my impression that you have been, when it comes to the clinical and the in vivo measurements, you have been looking mainly at increased blood flow or perfusion levels. Of course, there are also situations clinically where you could be interested in a reduction in perfusion. Can you tell me if the method that you have been using is equally sensitive in detecting reduction in perfusion, if your system is suitable for this application as well, or if you would need to make further optimizations for it to be suitable for that?
Well, that's quite an interesting question. I would like to remind that the focus of our study was to detect the relative movements. We do know that when we have egg movement artifacts, there's always an increased perfusion level, which is a result of extra blurring of speckles within the exposure time. What we have detected in one of our studies, we just looked at a speckle contrast map when we translated the system, just moved it and measured perfusion from speckle contrast. And we saw that when we apply speed, we will see a linear increase. So, and then it means that if at zero speed, your perfusion level is this much, as you apply movement, you will see it increasing. For a patient with decreased amount of, for instance, perfusion because of certain disease, we are here. And then we will also observe an increase. So our study is all about detecting this velocity and compensate the movement artifacts. But what we also saw that as the level of perfusion at zero speed or without movements increase, the slope of the line also tend to increase, which means that for different baseline perfusion levels, we need to think about a model that takes into account how to deal with this. That's short answer is that it needs further research.
Thank you very much. I have no further questions.
You're welcome.
Thank you very much. And the discussion will be continued by Professor Stirenborg from the University Medical Center in Amsterdam. Professor Stirenborg, please.
Mr. Chairman, dear candidate, also my maybe I should put the sound down a little bit. Yeah. Also, my compliments for a beautiful thesis. I'm very honored to be able to exchange some views with you in the next few minutes. Especially because I'm not an expert in speckle, and I was somewhat overwhelmed by the theory, because I should be able to understand it, but still, it's quite a thing to go through all of it. So I sort of skimmed through the surface, and then suddenly on page 82 you state that you assume single scattering. And then I thought, we know it's diffuse light. It should be multiple scattering. So I wasn't doubting you, but I was doubting my own understanding of what I read. So could you please explain a little bit how you come to mention single scattering there?
Highly learned opponent, I would like to thank you for your compliments and very interesting question. If I understood correctly, your question is about how single scattering is considered in our study while multiple scattering is what happens in practice. I would like to say that the equation 5.5 holds for two situations. That you can say the velocity that we estimate is inversely proportional to the correlation time for two cases.
Excuse me, I want to interrupt. If you write on the left side of the board, I cannot see it.
Okay, so
you do it on the right side.
Oh, sure. Well, the discussion was that the velocity that we estimate is inversely proportional to the correlation time, and the field correlation, we call it G1, is modeled by an exponential decay of 1 over its correlation time. So the increased correlation time causes decrease of the field correlation. So this holds for two cases. The first case is that you have single scattering and an unordered motion, such as Brownian motion. The second case is that you have multiple scattering, whereas you have ordered motion. So ordered, what we have studied here is a static objects. Static objects means we have basically ordered motion. We just apply translation. So we satisfy this. Then we can consider multiple scattering there. So what we are doing, we're using this to predict perfusion. And our case for phantom study, static phantom study does hold for the case of ordered motion plus multiple scattering. So how to apply this in practice? In practice, we have unordered motion. Unordered motion comes from random movements of hand plus random movements of red blood cells. And then we have a multiple scattering, which means that we are in this regime. So that complicates the problem. And for that case, the field correlation function cannot be simply explained by an exponential decay. So in order to be able to go ahead, we considered this case and found some linear relations. But for sure, if you want to apply, if you want to use it in practice to predict movement artifacts on tissue, we need to consider that, and that complicates the problem. The research should be continued.
Okay. Well, thank you for the answer, but I can understand that the scattering events that introduce the speckle, the change in speckle due to the speed, that is much more scarce than all the other scattering events. But my second question is about speed change. So in a phantom, I can understand that you control all the plumbing, and that if you want to increase the speed, you simply increase the pressure. But if you do that in a blood vessel, then we know that if you increase the pressure, that the blood vessel swells up, and that you also, or very often, also get more blood in your blood vessel, which means that your average photon path length will change because of absorption, and the first order approximation that you just described, this linearity, would still hold, but it would have a different proportionality constant. Or am I missing something? I mean, is it true that it is also sensitive to blood volume changes that you're officially not considering? I mean, it's
Thanks for your interesting remark. For sure, when we have a field correlation function which is not simply explained by an exponential decay, we cannot predict perfusion in a linear manner. And that's what happened in tissue itself. So in order to comment on that, I would say that so you mentioned that when we have a higher blood flow, higher perfusion, we have a different path length, which means that because of absorption, what we in one of our curves on the first chapter, we saw that when we have different scattering levels, when the scattering level is decreased, the movement artifacts or speckle contrast drop increases. So that means that an accurate prediction of perfusion is not only a function of what the perfusion level at the beginning is and what the detected speed is, but also what the scattering level is. And our prediction for absorption, so here we talk about scattering, but our prediction for absorption was something similar, is that when you have lower absorption, you will observe higher drop in speckle contrast. So that means that the movement artifacts or the perfusion added is a function of your applied velocity, your scattering coefficients, your absorption coefficients, and as you said, the concentration of red blood cells, or let's call it the volume. So these should also be added. I'm not going to again say that it needs further research, but that's really is. And so we try to make things as simple as possible so that we could go ahead.
Okay, well, on the same page you also state that it's not your purpose to quantify the blood flow. So that's a safe statement. But what do you have to do if you do want to make it more quantitative? Are there possibilities for that?
I would like to ask what you mean by quantitative.
Well, that you really know the speed,
the absolute
and not
speed.
just a relative change.
Yeah. Okay. Absolute speed. Well, when we talk about exactly how much blood we have liter per minute, of course, volume tissue to talk about perfusion, it's all about knowing not only what the relation between predicted velocity is related to correlation time, but also what factor here we see. As the extension of chapter 4, we have explored it further, and we found an inequality of velocity and correlation time, and a characteristic length of an area function, which takes into account the magnification of the system, the wavelengths of light source, and the distances. So here we can put one step towards talking about exact values, but it's knowing about how blood flows move. So we do know that we have Brownian motion. You don't see it here, but you should see it here that red blood cells move in a random order, as well as in a certain direction within the capillaries. And the capillary structure is also not straight. So all these complications requires us to first knowing what we image. When we know what kind of structure we are imaging, we can make a better estimation. But at this moment, if you see a perfusion map, that's all relative. And that's the safest way to go. Yeah.
Well, I've been seeing perfusion maps for several decades now, and they're all not quantitative. And that is sort of a pity, because I think it's a very powerful technique. Do I have the time for another question, Chairman?
A very short, and also then a quite short answer as well, please. Yes.
Okay. Well, would it help to do speckle imaging with two wavelengths? Two wavelengths that would have roughly the same. Well, they would see the same particles moving, but they would have a different absorption coefficient. and therefore you would have two different speckle images of the same moving objects. Would that give you a clue to more quantitative measurements?
Well, thanks for your question. Our focus initially here is to know how much movement artifact is added, to subtract it to get a more realistic perfusion map. You are focusing on using two wavelengths to get more quantitative data, means going towards absolute blood flow prediction. My quick answer would be, as long as we have we establish a relation between wavelengths or a spectrum with absorption, that of course exists, but how absorption correlates to movement artifact or perfusion, then we can consider that and make use of using a system which performs multispectral or multi-wavelengths. To establish, I would say, a robust model. Yeah, that could be an option. Thanks. Yes.
Okay, thank you very much. I give the word back to the rector.
Thank you very much. And the discussion will be continued by Dr. Sacher. She's a dermatologist and also researcher from the Radboud University Medical Center.
Dear candidates, first, also, I would like to congratulate you with your beautiful thesis, which I've read with much interest, although I must confess that I only read the parts with the clinical parts. The other ones were very difficult for me to understand. I'd like to also congratulate the promoter and the rest of the team, and thank you also for the invitation to participate in the opposition. In chapter 3, you described the influence of wavefront types on the movement artifacts. And you showed that the scrambled waves lead to significantly larger movement artifacts than the planar or the spherical waves. And then in chapter 5, which we worked on together, you examined the performance of the handheld LSCI compared to the mounted one in psoriatic skin, and you used the spherical wavefront, which causes least movement artifacts when rotating the LSCI system. And my question to you is, why did you choose the spherical wavefront in the LSCI system and not the planar wavefront, which causes least artifacts in translating the LSCI system? Because I can imagine that both the physicians and the patients have also translational movements and not only rotational movements. And would that also have changed the outcomes of your study?
My learned opponent, thank you for your kind words and interesting remark on use of spherical waves in our system, but not plane waves. Although we showed that on average, these are plane waves that causes least amount of movement artifacts. In response, I would like to say that the question goes how to make plane waves. And what is our requirements? Our initial and important requirement is that we would like to image a field of 10 centimeters by 10 centimeters. If you want to illuminate this area with plane waves, it means that we need to have a bulky optic, either a lens of diameter of that size or a mirror of diameter of that size. That means that our system becomes bulky. And that just doesn't go well with our initial requirement to have a system as compact as possible. And we do know that it influences our result. We measure a higher magnitude of movement artifacts, and that the percentage we have written exactly on the table, it has some 10% difference, I think, when we measure on static objects. But then we go further to model them. If we can establish a good analytical model for the movement artifacts, we are able to predict and compensate that residual movement artifacts caused by using a spherical wave but not a plane wave.
Thank you. Another question is about the post-processing. What you showed in chapter 5 is that a proper post-processing, you can find agreement between the mounted measurements and the handheld measurements. But as you know, in the study, in the clinical practice, we want a post-processing very quickly, preferably in only a few seconds, and also, of course, in the hospital and not in the Twente University. So in the future, if we could use a handheld system in our hospital, how would you see this? Do you have any idea how to adapt the HAPI system in order for us to use it very quickly in the hospital with the post-processing also in the hospital?
Thanks for your question. I try not to forget the first part of your question, but it didn't happen. So I'm going to start by answering the second part, which is about how fast can we implement the post-processing part. So the response is that's the first time we are using this. So we had fortunately a good mathematical colleague, a mathematician who helped us doing the tracking directly on speckle images, so that we don't grab images with RGB camera as well. So the advantage was that the single speckle frames were used for purpose of tracking as well as perfusion imaging. It does need markers also, so that's also a disadvantage. If you did the markers on the skin, and we're glad that those markers can be used to track, but it's not the case always. For instance, you image burns, you don't have markers. So first problem is that we don't have markers, so we should think about another tracking or tracking algorithm. To make it faster, it's all about programming and software. If we can use a better software that helps us to automatically detect these markers and track them, then we are one step closer to make it faster regarding analysis. Then you can use it in a hospital while previewing a lesion in handheld mode to track and just focus on a certain region and monitor its perfusion. I would appreciate if you could repeat the first part of your question.
Well, actually, it was especially how you would make it quicker and that we can use it in the hospital immediately and not first send the results to the University of Twente. So I think you also answered that question. Thank you very much.
You're welcome.
I don't know, Mr. Rector, do I still have some time to ask another question?
Yes, you do. Yeah, you do have time for another question.
Okay.
Yeah.
I'm going to write down
then
your
I'd
question.
like to ask you something about... Sorry?
Go ahead. I'm listening. I'm going to write it down not to forget.
I want to ask you something about chapter 6, which I was very surprised and very interested to learn about this multimodal imaging technique. And what you showed us in the chicken vasculature, how you can show everything about this vasculature. So I was thinking, as you know, in the psoriatic skin, we are looking for the hot spots and the cold spots. And the hot spots are the sites where there is a high flow, and the cold spots are the sites where there's a low flow, all in the same psoriatic plaque. And we used your beautiful LSCI system to locate these hot spots and these cold spots based on the flow we saw with the LSCI system. And what I was wondering now is, could we also use this side stream dark field microscopy and white light imaging in a live patient, so in a real psoriatic patient, and would that help us to also see microvessel geometry and vascular dilatation? And could you elaborate a little bit on, would it work in a psoriatic patient? If so, how would you do this experiment, and what would you expect from it?
My learn upon it. Thanks for this nice question that brings the connection of chapter 6 of my thesis compared to the rest. In response, I would like to say that I'm glad that the perfusion maps we showed could help you determine hot spots and cold spots by one look. Your question was whether we can also use white light imaging as well as side-string dark field microscopy to build up a multimodal imaging system for psoriasis patients. I would like to say that white light imaging is already used, so you do get color images, one single color image. So yeah, you can then by the naked eye on the color image investigate what the structure of that lesion is and get some complementary information from the LSCI system. Regarding SDF, I should say that SDF is not completely a non-invasive. It depends how we determine non-invasive measurements, but it does touch the skin. So if it's fine to touch the lesion, you can observe individual red blood cells moving through capillaries with a maximum field of view of 1 by 1 millimeter. So the disadvantage is that you don't have a wide field of view. So if you do want to know what is the status of that capillary in that 1 by 1 millimeter square area, for sure SDF is a good technique to use. But we are not who developed and invented SDF. We just used the probe that existed.
Does the answer satisfy you?
I'm very glad and thank you for the nice answers there. Thank you.
Thank you very much. And the discussion will be continued by Professor Offerhaus from the University of Twente.
Thank you, Mr. Rector. Dear candidate, I also enjoyed your thesis very much. I'm always impressed by work that goes all the way from the fundamental to the actual application. But several people have now said that the theory part was quite hard, and so I would like to discuss that bit and try and simplify it to look really at the physics of speckle formation, and especially in the case this is what physicists always do. They try and reduce it until you can actually understand it. So if we think about the K vectors that come from the scattering, from a single scattering, and now we have a source here, and we're hitting this particle here, and we have a camera here. What now happens if I have a rotational artifact? So we're leaving everything static. There's nothing moving yet in the object, but my source rotates a little bit. I guess that means that the K vectors, that the whole scattering pattern shifts as well, right? Is that correct?
Highly learned upon it. I would like to thank you for your kind words. And I would like to say, yes, we should also consider what are our assumptions. We put both imaging system and detection system on the same panel.
Yes.
When we move, yes, K vector moves, tilts or rotates.
Our camera also rotates, right? So does that mean that to first order, and for this highly simplified system, if I just rotate, I get the same speckle image? So the speckle image is static despite rotating so if I also keep the pinpointing position the same, but I rotate, does that mean that in that case my speckles are static?
So your question is whether the speckle pattern stays static when we move both illuminating system and detection system towards as we certain
but we
axis.
don't move like this, because then the point that we illuminate flashes over the patient. What I'm thinking about first is if I'm still hitting the same point at the patient and I rotate like this.
Tilting it.
So I do have this. At some point you talked about an aiming point. So if I keep the aiming point the same and I rotate around that aiming point, would my speckles be static?
Okay. So your question is about the speckle dynamics.
Yes.
Not necessarily about the Doppler shift we observe. Static speckle dynamics, my quick answer is if we illuminate with spherical waves and tilt the system while looking at this spot, as we tilt, the incoming and outgoing wave vectors stay the same. And we, if the system is not scattering, if you only have surfaces scattering, ideally you won't expect any change in your speckle pattern.
Okay.
And that's what in one of the graphs on figure in chapter 2 you can see that the experiment with different wavefronts on a single scattering matte surface, the speckle contrast doesn't tend to show sensitivity to apply the speed, but because it's a practical situation, it does drop a little bit, but no, it doesn't. So
okay. And if we allow for a little bit of diffusion into the skin?
Then you do see a drop. Then the whole story of optical Doppler shift comes to play a role. And
but wouldn't that also still be the same? So if I allow for a Doppler shift, but I'm now rotating a little bit, so my incoming K vector changes, wouldn't my outgoing K vector, even after the Doppler interaction, also shift the same amount?
I think the incoming and outgoing wave vector is not a function of the medium, but the way we apply velocity. So the detected optical Doppler shift is the difference, the result of difference in incoming and outgoing wave vectors and the applied velocity. So this part stays the same, but it's all about the velocity.
So if you rotate with respect to the velocity, you get a change.
Yeah. Okay. Depends on how your particle moves. The one we model is all about translation, also ordered motion.
Yeah.
And that we have mentioned that I'm not going to repeat this again. That needs further study.
Absolutely. So one other question I have in this direction is if you think about the speckle pattern that you get, it's determined by this range of K vectors that you get in, and you can manipulate this by rotating your diaphragm. Is there like an optimum size of a speckle? Because I guess you want to resolve them on your camera to see change, so they shouldn't be too small. They also shouldn't be too large, because then you don't see them move, maybe. Is there an optimum? How do you determine it?
Yeah, I think Tom Knopf would love to answer this question. So on his behalf, I'm going to explain the experiment he did to determine a good diaphragm size to set for our handheld prototype. He did the experiment while we recorded speckle contrast as a function of diaphragm size.
Yeah.
We call it a D.
Try to keep the answers short and concise, as Tom would do probably too. Thank you.
So then you will see that the speckle contrast doesn't change when we decrease the diaphragm size. When it's when we open it, at certain point when we have two speckles added on the same pixel, the contrast starts to drop, and that point was the value of f8. So f8 is the numerical aperture
so you have to stay below this.
Yeah.
But is that only related
effective aperture size,
Is it only related to the chip, or is there anything involved in the patient?
It's all about the diaphragm size used in the imaging system.
Okay. Thank you very much. Thank you, Mr. Rector.
Thank you very much. And then the discussion will be continued by Professor Verdaasdonk, also from the University of Twente.
Thank you, Mr. Rector. Dear candidate, congratulations with your thesis, and also congratulations for your supervisors. And I'd like to continue with some other direction, and to see if there are any solutions for your problem, is the motion artifact. So one of the things you write in your conclusion is that you would have less scattering if you would move to, or that you would have less scattering or reduce it when you have less scattering. So a way to get less scattering is to go to longer wavelengths. And you're using now a wavelength about 671. But if you would move to in the direction of 800 nanometers, for instance, then would you have less motion artifacts?
Highly learned opponent. I would like to thank for the compliments you made in the beginning and the nice question you raised. The answer is we should go back to see why we used the wavelengths of 671, that's red. Because we are interested in movements of red blood cells, detecting those movements by observing dynamic speckles. If we shift from that wavelengths to another wavelengths, we run the risk that red blood cells absorb light, so we do not observe interference pattern caused by scattering. I would like to ask which wavelengths you proposed for us. Is it if it's going towards infrared? Then we still can work with LSCI system. Then we should explore what scattering coefficient we get when we go to shift towards the infrared wavelengths. And we are interested in having higher scattering, so we detect lower...
There is a contradiction in this. So you want to have the best signal for scattering, and on the other hand, you could solve your problem a little bit. So I have another solution, maybe. So you have a handheld device, which includes as well as the illumination source and the camera. What if you would take the illumination source out, put it on a tripod, so it's static, and then only move the camera around? Would that be a solution?
Thanks for this suggestion. That means that our handheld system won't be by itself a handheld. So then we have a half-mounted part. So if we don't move the detection system, I would say if it even becomes worse, because when you move, your both Ki and Ks move together. So the relative change that it appears that causes the observation of optic Doppler shift is lower when we separate them, because when we separate them, we have now a reference arm, another one starts moving. So I can, as a quick answer, say that won't help in terms of functionality of physics, and when we have another system as a mounted part, like for it to only illuminate.
So we make it worse.
I assume that we make it.
Okay. Worse, yes. So, but then let's talk about the handheld system. So, well, we have a dermatologist also in this committee, but I like your answer. But is it really an advantage to have a handheld system? I've seen the system, and it is pretty bulky. It is quite heavy still. So, why would you really aim at a handheld system? Did you ask physicians what they would prefer? Or
thanks. This is the question I really like, because I've received it as long as I remember joining this research. My quick answer is that you would like to measure on areas which is, for instance, include knees or here. So you have patients who are suffering from diabetes, and so sometimes they're obese and they cannot have certain maneuvers under the system. So the initial and the most important advantage it brings is that it makes the measurement easier. That's the first one. Second one is that you want to take the system in the operation room, in which everything is quite congested. So people are around, and I haven't been there yet, but I can imagine that you do need to have a small system to do the measurements in a reliable manner, of course. We did ask our colleagues, our dermatologist colleagues, about this. It is definitely an advantage. So but it's also the matter of movement artifact. If you say we're going to bring something for you that's operating easy but gives you unreliable results, I guess that they prefer the mounted system itself. But if we can show that it does measure on a reliable manner, then for sure they would love it. And although they did our study with our prototype unmounted because of not knowing whether it's going to work with on a handheld mode.
Yeah, there are systems you can put on an articulated arm, which is in quite balanced, so you can easily move it around and have it at one position. But okay, then we are still going for the handheld.
Yes.
What if I would use a smartphone? If I'm looking at the specs of your camera, that are pretty much comparable what you can achieve with the cameras in smartphones nowadays. And in addition, the computational power of a smartphone is pretty impressive. So would it be possible to replace part of your handheld device just by using a smartphone?
Well, thanks. If you can convince me that a smartphone camera can work as good as our bachelor cameras in the lab with such a high quantum efficiency and signal-to-noise ratio, then I would say for sure I would buy it and we'll go on. The thing is, I've tried it with normal smartphones. You will never get such nice speckled patterns as we get with our... But those bachelor cameras are not the big... But they are just not a part of a smartphone.
Would it be in relation to the size of the sensor then, or?
It has to do with the technology itself and what's important when you're designing a system. So.
Thank you, Mr. Biedel. Can I ask the candidate and his paronyms to take their seats in the room, please? And I adjourn this public meeting of the Doctorate Board of the University of Twente. Please be seated. And I reopen this public meeting of the Doctorate Board of the University of Twente. Can I ask the candidate and his paranymphs to stand before this table? Het college voor promoties van de Universiteit Twente, door ons vertegenwoordigd, heeft kennis genomen van uw proefschrift en heeft uw verdediging gehoord. Het college voor promoties heeft besloten, krachtens artikel 7.18 van de Wet op het Hoger Onderwijs en Wetenschappelijk Onderzoek, u de graad van doctor te verlenen. Ik verzoek de promotor zich van de opgedragen taak te kwijten.
Uit kracht van de bevoegdheid ons toegekend door de wet en namens het college voor promoties bevorder ik Ata Chizari tot dokter en verleen ik u de rechten die verbonden zijn aan de dokterstitel. Ten bewijze hiervan overhandig ik u het diploma, ondertekend door de rector magnificus, de secretaris van de promotiecommissie en uw promotor en bekrachtigd met het zegel van de Universiteit Twente.
Zeer geleerde dokter Chizari, mag ik u ook namens de universiteit feliciteren met de behaalde waardigheid. U hebt vanaf nu het recht de dokterstitel te dragen. Uw dokterstitel betekent dat de samenleving op de kwaliteit van uw oordeel kan vertrouwen. Dat u integer en transparant handelt en dat u onafhankelijk communiceert over de resultaten en de maatschappelijke relevantie van uw werk. Waardeer de dokterstitel als een eervolle onderscheiding. En een welverdiend voorrecht, maar vergeet daarbij nooit de plicht die zij u oplegt jegens wetenschap en de samenleving. Ik heb gezegd. En dan geef ik nu graag het woord aan de promotor voor het uitspreken van de laudatio.
Dr. Chizari. Het is even wennen, Dr. Chizari. Mooi dat ik je zo mag noemen. Ik wil je hierbij hartelijk feliciteren met je titel, maar vooral ook met wat daarachter zit. Met 4 jaar hard werken, het resultaat ervan, een aantal hele mooie artikelen, die inmiddels ook al zijn gepubliceerd grotendeels, en een geweldig proefschrift. En dat dan hier verdedigen op de manier waarop je dat vandaag hebt laten zien. De titel is belangrijk, maar vooral wat je allemaal gedaan hebt, wat je zelf geleerd hebt en wat je hebt bijgedragen aan de vorming van studenten, aan de wetenschap, aan het verder ontwikkelen van de technologie. Dat zijn dingen die belangrijk zijn en daar wil ik je met name ook mee feliciteren. En ook mijn felicitaties voor Moti, een hele bijzondere dag voor jullie samen. Also, my congratulations to your beloved ones, in particular your mother. You can be very proud of your son for what he has achieved, but in particular for who he is as a person, as a human being. Eerst even over het werk, over het project. Ik vond het zelf een ideaal project. Er zat van alles in. Technologisch onderzoek, het maken van een apparaat, fysische modelvorming, maar ook heel veel samenwerking met de RAM-groep, met de dermatologen in Nijmegen, met de groep van Jeroen Raukema. En niet alles lukte. Lang niet alle ideeën die we hadden, die konden worden gerealiseerd. Maar er is ontzettend veel wel gedaan en ook wel gelukt. Dat betekent dat er ook vaak heel veel tegelijkertijd moest gebeuren. Op allerlei gebieden. En mooi dat het je gelukt is om al die contacten te onderhouden. En dat uit al die samenwerkingen ook echt resultaten zijn gekomen. Maar daarom wil ik ook iedereen die heeft meegedaan bedanken voor de samenwerking. Als je naam gaat noemen, dan loop je al het risico om mensen te vergeten. Dus van tevoren vast excuses daarvoor. Maar Tom, Marieke, Mirjam, Ferdi, Beryl, Prasanna, bedankt voor de samenwerking en voor wat er uiteindelijk tot stand is gekomen. Ik wil ook nog apart noemen dat je heel veel met studenten hebt samengewerkt. In de groep van Ferdi van der Heijden, maar ook eigen afstudeerders. Daar heb je veel tijd aan besteed en daar heb je ook heel veel voor teruggekregen. Maar ik wil ook Klaas, Tommy, Sven, Wilson, Stijn bedanken voor hun bijdrage. Verder wil ik het onderwijs noemen. Je hebt een bijdrage geleverd aan de vakken Biomedical Optics en Ultrasound. Dat heeft je best heel veel tijd gekost. En je wil het ook heel graag, maar ik wil je er erg voor bedanken voor wat je in die vakken ook gedaan hebt. Het was en het is nog steeds fijn om met je samen te werken. Je bent een goede planner. Als je iets zou gaan afleveren, dan gaf je ook altijd aan wanneer het ging gebeuren. En daar hield je je ook altijd aan. Altijd tot aan deze week. Want uitgerekend deze week is het je niet gelukt om je laatste manuscript aan te leveren. Maar dat zij je vergeven. Het is een spannende week waarin heel veel door je hoofd speelt. Dus dat zie ik door de vingers. En ik heb morgen toch iets te lezen, heb ik al gezien. We hebben heel veel discussies gehad. Onder andere over het model van hoofdstuk 4 en over de vormgeving van de experimenten. Je had heel veel ideeën. Goede ideeën. En soms ook slechte ideeën. Maar ook dat is prima, omdat je daar heel open over bent. En dan kan je erover praten en dan kom je verder. En verder was je gewoon heel gretig. Dat hebben we ook vandaag weer gemerkt. Je wilde graag resultaten presenteren. En ik denk dat je in de groep kampioen short updates geven bent. En je bent zeker kampioen de eerste vraag stellen. Het was dat vandaag alleen de commissie vragen mocht stellen. Anders had jij graag de eerste vraag gesteld. Heel bijzonder vind ik de manier waarop je in de Nederlandse samenleving hebt genesteld samen met Moti. Je wilde Nederlands leren en dat heb je gedaan ook. Je begon hier op 1 februari 2017 en op 31 mei 2018 voerden we de eerste werkbespreking helemaal in het Nederlands. En toen je op precies de goede momenten helemaal goed ging zeggen, dacht ik van dat komt wel goed met het Nederlands. En op een gegeven moment kwam je zelfs met de vraag, is het nu thuiswerken of van huis uitwerken? Nou, dan weet je dat het echt goed zit. Ik vind het knap, zoals je dat gedaan hebt. Het staatsexamen Nederlands als tweede taal, kennis van de Nederlandse maatschappij, oriëntatie op de arbeidsmarkt. Je hebt het allemaal gedaan. Ja, jij doet dingen met overgave. Fietsen, zwemmen. Je hebt al een marathon gelopen. De grote triathlon staat zelfs op je lijstje. En je doet aan duiken, diep duiken. Eén keer dacht ik van, wat doet hij nu? Dat was toen ik op Twitter een filmpje voorbij zag komen waarop jij je uit een vliegend vliegtuig stortte. Het is goed dat je bepaalde dingen als promotor gewoon niet weet. Althans van tevoren. En ik begrijp dat je het daarna ook nooit meer gedaan hebt. Te gevaarlijk. Ja. Voor ik afsluit heb ik nog één vraag. Hoe is het afgelopen met de kip? Of was het een haan? We hebben het er nog wel eens over, maar misschien wil ik het ook nog helemaal niet weten. Ik wens je hier nog een hele goede tijd aan deze universiteit. En in ieder geval heel fijn dat je in ieder geval nog een half jaar kunt blijven. Ik wens je alle goeds bij het nadenken over je verdere toekomst. En het gaat je goed samen met Moti.
Dank u wel. Ata, ik wil je ook van harte feliciteren met dit resultaat. En uiteraard ook je echtgenoten en je moeder en familie en bekenden meenemen in de felicitaties, de promotor. En ja, als voorzitter maak je altijd even kort kennis met de kandidaat. En voor de muzici, er zijn mensen die naar pianoles komen en dan vraagt de pianodocent, speel eens even een toonladder. En dan weten ze al of je talent hebt of dat je gewoon goed piano kan spelen zelfs. En met Ata spreek je 2 minuten en je kijkt dus naar het proefschrift en dan weet je al, dat zit wel goed. Dan heb je ook meteen al een indruk, dat is een echt goede kandidaat. En dat is vandaag ook gebleken uit de zeer mooie verdediging, waarbij je ook goed gebruik maakt van het schoolbord bijvoorbeeld. Dat vind ik erg mooi, als dat kan. En het is ook een prachtig voorbeeld van multidisciplinair onderzoek. Fysica zit erin, engineering, klinische metingen. Echt een prachtig voorbeeld van translationeel onderzoek, zoals we dat heel graag doen aan deze universiteit. Veel vakgroepen doen dat, zeker ook de groep van professor Steenbergen. Dus dat is ook heel mooi. En ik hoop natuurlijk uiteindelijk dat het ook echt een plaats gaat krijgen in de kliniek. Dat is niet eenvoudig, dat kost vaak ook nog langere tijd. Maar het team is in ieder geval uitstekend. En ik wil je heel veel, nogmaals geluk wensen. En ik hoop dat je wellicht langer dan een half jaar aan deze universiteit kan verblijven. Dat kan ik weinig beïnvloeden, behalve mijn hoop daarvoor uitspreken. Nogmaals, van harte gefeliciteerd. En ik wil je vragen, samen met de paranimfen, om weer in de zaal te gaan zitten. En dan, voordat ik deze bijeenkomst beëindig, een korte huishoudelijke mededeling. We gaan zo dadelijk de zaal verlaten. De pedel zal ons voorgaan, gevolgd door de jonge dokter, de paranimfen en de familie, dus de mensen hier op de eerste rij. Dan volgt de commissie en dan de andere gasten. En hiermee beëindig ik deze openbare zitting van het College van Promoties van de Universiteit Twente. Ik begrijp net dat de jonge dokter inderdaad ook nog graag de digitale aanwezigen wil bedanken. Dus, Ata, ga je gang. Ja.
Beste Marieke en Dick, ik wil graag u bedanken voor uw bijdrage en mooie vragen. En bedankt voor uw tijd, dat jullie bij zijn. Ik heb heel geniet. Bedankt.
Heel erg gefeliciteerd.
Van harte gefeliciteerd, Ata. Geniet er heel erg van en hopelijk zien we elkaar nog. Het was heel prettig met je samenwerken en het was ook erg fijn om bij je op positie te kunnen zijn. Een hele fijne dag gewenst nog.